1, 2, 3, 4. I believe they have in here, this is where they have the fundamental accounting principle in here. Like, I've got 5, options of this and 3 options of that, and 2 options of this. How many different possibilities? They put that in this section where I think it goes a little bit better in the other section. That's why I put it in a little bit before. But there are some additional things that we'll talk about today that kind of are not very similar to the addition and multiplication rule. I thought the fundamental accounting principle ties right to the multiplication rule, so that's why we did it then. All right, so what we're going to be talking about basically today is permutations and combinations. Okay, permutations and combinations. Permutations. The word permutation is basically just means an ordered arrangement of objects. A permutation is just an arrangement of a set. In our statistics language, we have to say, well, we have to tie in that piece about it being ordered. It's an ordered arrangement of objects, and that is really what matters here. And that is what's going to differentiate it between a combination. The word ordered, okay? Ordered arrangement of objects. The number of different permutations of n distinct objects is n, or n factorial. It's just the very excited way to say n. It's n factorial. That exclamation point is called factorial. This, we've all seen that. Have we all seen that before? Maybe, maybe not. Oh, close. Times. Yeah. So that factorial symbol, and I believe I got it over here. I don't wanna, that factorial symbol is just basically a way to say that the n value times every integer below it. Or not integer, every whole number below it. Natural number below it. If I say whole number, it includes 0. Every natural number below it. So if I say like 3 factorial, that is 3 times 2 times 1. So 6. Right? So if I have 3 things and I want an ordered set of 3 things, I can have 6 ways of putting those 3 things. So that means if I, think about it this way. If I have the letters A, B, and C, there are 6 different ways to arrange the letters A, B, and C in terms of order, right? We have ABC, ACB. Let's start with B. B, AC, BCA, CAB, and CBA. I am not changing the components of my set, right? My set is still just 3 things. What I'm doing is arranging them in orders, right? And I have 6 different arrangements that I could have. I have 3 factorial arrangements of them. Okay, 3. So 6 different total arrangements. All right, so let's talk about some factorials. What is 5 factorial? Now, you guys will be allowed your graphing calculators and your graphing calculator, or your red calculator if you want to borrow a red calculator, or you borrow my graphing calculator. They have the factorial symbol on it. And I say that now I'm second guessing. Do the red calculators have a factorial? I think they do. Yeah, there's the PRB button, and then you have NPR, NCR, and then a factorial symbol. But honestly, you could just figure it out doing it the long way too, right? Especially if it's just like 5 factorial or something like that. To get into it in your TI-83s, what was it, 5 factorial? You just type the number 5, and then right here, this math button, and then scroll right to probability, PRB, and then you have NPR, NCR, and then the factorial symbol. So 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. 5 times 4 times 3 times 2 times 1, which is 120. So if you have 5 different things, A, B, C, D, and E, and you're going to arrange them in different ways, you have 120 different arrangements that you could possibly have with those 5 things. Okay. So what would 6 factorial be? Well, isn't that just 6 times 5 factorial? So that's 6 times 120. Right? Let's just do that times 6. 720. Follow me there? The definition of n factorial is really just n times n minus 1 times n minus 2 times 1 until you get all the way down to 1. All right, so what's 1 factorial? 1. Ooh, what's 0 factorial?
Undefined.
It's actually defined to be 1.
Why?
Why is that the case? Ooh, I've got a little funky proof of it here. I have this. Oh, yeah, because n factorial is n times n minus 1 factorial, right? We kind of saw that right here, right? Wouldn't you guys agree? N factorial is really like n factorial times n minus 1 factorial. What is 1 factorial? 1, right? Isn't that 1 times 1 minus 1 factorial? Right? If we put that in that statement, well, this is 1 is equal to 1, which is essentially 0 factorial. So what is 0 factorial? Divide over the 1. So 0 factorial is 1. That was really kind of slick proof of it. Honestly, it's just defined to be 0. It's one of those things that like you just got to know. Just got to know that like anything to the 0 power is just 1, right? 0 factorial is just 1 as well. All right. A bowling team has 6 players. How many different bowling orders can there be if all 6 are bowling? I'm not choosing a set out of them. All I'm saying is that we've got 6 different bowlers. How many different orders can they go into? And the key word being orders, right? I'm not saying they're all going to play, or I'm saying they are all going to play, but I'm saying I want to know the different orders. I'm not saying like how many different teams could I make. I'm saying the orders of which they are bowling. Well, that would just be simply 6 factorial, which I believe we said 720, right? There are 720 different ways that we could make that team. You know what's interesting here is that I really could have thought about this as like the fundamental accounting principle, because, you know, 1, 2, 3, 4, 5, 6. Okay, I choose my first bowler. How many different options do I have? 6 different options for my first bowler, right? After I've removed them, how many different options do I have? After I remove them, which isn't that just 6 factorial?
That's so great.
Right? So we were kind of already doing factorials, we just didn't really know about it yet. Right? And we were saying, oh, you know, like I think we did this with like the passcode thing, right? Couldn't repeat numbers or whatever it may be. Oh yeah. Gotcha. Oh please. You have something to talk about. Rhode Island, either a road nor an island. Go. Oh, you're ready.
Actually, I think it was that. Okay. I didn't read all chapter 3, but like I listened to the audio.
All right. 8 friends are walking down the street, one next to the other. How many different ways can they be walking? 8 factorial. Right? 8 factorial. So in this case, 8 factorial is big number, 40,320. I could have 40,320 different arrangements of my friends, of all 8 friends. Make sense? Bigger the number, the more it grows. Yeah, really, shoulder to shoulder. All right, now what if I said, okay, I've got 8 friends, and I'm going to choose 4 of them. How many different arrangements can I make? See, now what we're going to be doing is taking specific numbers of them out. The number of permutations of n distinct objects taken are at a time. So basically like saying I've got 10 different people. I've got this class. I am going to take 3 of them. I'm going to take 3 of you guys at a time. And I am going to make a president, vice president, and a secretary out of each of those picks. How many different ways can I make that? That's permutations. Because first of all, I put them in placements, right? I said the first person I was going to pick was a president. The second person was going to be the vice president. The third person was going to be the secretary. And if I chose those same three people, but put them in a different order, would that change the outcome? Yes, it would. So therefore, order matters here, right? Order matters. So how do we calculate that? Well, we calculate that by taking n factorial divided by n minus r factorial. N factorial divided by n minus r factorial. Now, here's the thing. I'm going to talk about it with respect to the equation. However, you guys have that NPR function in your calculators. I'm not going to take that away from you. Okay? It's there. Right there. Okay? So all you really need to know is where that button is. But the nice thing about it is that you've already done this before. Okay? You've already done this before. You've got 10 numbers, and you're going to make a passcode of 4 numbers. Didn't we do that already? Same type of thing. Right? That is the exact same type of thing. Let me see it. I don't want to get ahead of myself. Yeah. We'll do it here. We have 8 different plants, but only room for 3 of them on the shelf. How many different arrangements are possible? How many different arrangements are possible? Well, if I really want to set this up, this would be 8p3, right? This is a permutation. By definition, this is a permutation. How do I know that? Well, because if I choose my cactus and my iris and then my just plants. What's another plant? A daisy. Would that be different from daisy, iris, and cactus? Does it look cactus? Does it look different? Yes, that is a different outcome, right? So if I change the order, it gets me a different outcome, right? That's why it's by definition of permutation. Okay, so this is essentially 8 factorial divided by, well, if I take n minus r, 8 minus 3 is 5 factorial, right? Now, what's interesting is what happens next. Isn't 8 factorial 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? What's 5 times 4 times 3 times 2 times 1?
5
Yeah. What do you see in both numerator and denominator? Yeah. Right? So really, this is just 8 times 7 times 6. So it's relatively easy to compute, right? 8 times 7 times 6. Oh, but
Oh no.
8 times 7 times 6 is 336. Guess what would happen if I went in? Now, I guess it's important to know how to plug in 8p3. 8, you type the number 8 in, and then you go to math, PRB, second option. So you got to have your 8 plugged in first, and then 3. Bingo. There it is, 336. Right? Now, here's what's really cool. We have 3 different places to put a plant, right? How many different plants do I have to choose from in my first option? How many in my second option? How many in my third? Isn't that the same thing we just did? So really, we were doing that when doing our passcode problem. We just weren't really calculating it as a permutation. Good. Let's take another one. How many different 4-digit codes are possible if numbers are not repeated? Hey, this sounds familiar, right? How many different passcodes are possible if numbers are not repeated? Okay, I know we've done this by just like counting blanks, right? But let's do it as a permutation. Because wouldn't you guys agree that order matters here? 1, 2, 3, 4 is a different passcode than 4, 3, 2, 1, right? One will unlock it and one will not. So therefore, I do have order mattering. How many different total possible numbers do I have? 10 options, right? How many am I picking?
4.
So it's essentially just 10p4. 10p4. which is 50/40. Okay, let's do this the old way, right? I have 10 here, 9 here, 8 here, and 7 here. 10 times 9 times 8 times 7, 50/40. Make sense? Okay. All right, so what if I say, well, the order doesn't matter anymore? Oh, no, sorry. I'm not doing combinations yet. I'm doing distinguishable permutations now. So what if I have like groups of things that are all similar? Right? Maybe I had, I was thinking about it in terms of I've got a group of freshmen, a group of sophomores, a group of juniors, a group of seniors. And I know I wanted to pick, 3 sophomores, 2 juniors, 5 seniors, or something like that. I have groups of things. This would change it a little bit because now we have what are called distinguishable permutations. The number of distinguishable permutations of n objects where n1 and n2 are different types, different sets, different groups, and so on. And I could have an infinite amount of groups. K amount of groups, they call it. What I can do there is multiply all of the permutations together on the bottom. And in the numerator, I just have n factorial, where n is my total amount. So if I've got like 50 kids that I'm picking from, 50 factorial goes in the numerator. And then in the denominator, if I wanted to pick, 3 freshmen, 2 juniors, 5 seniors, well, then that would be in the bottom, 3 factorial, whatever numbers I chose there. I don't remember. Okay, let's take a look here. Stacy wants to plant some trees along her driveway. She wants to plant 5 cherry trees, 3 dogwoods, and 4 pears. So she's got how many trees in total? 12 trees, all said and done, right? I've got 12 trees to plant. And now? Okay, are the cherry trees distinguishable from one another? No, right? I have all of those cherry trees are essentially the same thing. All of these 3 dogwoods are essentially the same thing. So it's not necessarily 12 factorial, right? Because 5 of them are all cherry, 3 of them are all dogwood, and 4 of them are all pear. So it's not truly, it's less than that. It's not 12 factorial. It's actually smaller than that because, putting the cherry tree, the first cherry tree first, or the second cherry tree first, or the third or fourth or fifth cherry tree first is all the same thing. Right? So here's how we compute that. We take 12 factorial in the numerator, our total amount, divided by the number of sets of things that I have. Five factorial times 3 factorial times 4 factorial. All right, so 12 factorial up in the top, excuse me, is, whoa, that's a big number. Couldn't I reduce that down?
That's like a lot.
I know, but like thinking about it this way, I wonder if I can reduce that a little bit. Nah, that's okay. We'll just do it in with the strict numbers. What is this? 479 million. 479 million. 1 and then 1600. 0, 0, 1, 6, 0, 0. All divided by 5 factorial times 3 factorial times 4 factorial. $17,280. Okay, let's divide those numbers. 479,001,600 divided by 17,280. 27,720. Yep, that's what I got. Those are the amount of different ways that I could plant those trees, which is very different from 12 factorial, right? 12 factorial, I would have had over 479 million different ways to plant those 12 trees. But I know that 5 of them are all cherry and that doesn't change anything, right? Planting those doesn't change anything in different orders. They're still all cherry trees. Okay. John goes to a donut shop, knowing that he's going to buy 5 glazed, 3 blueberry, 2 chocolate, and 2 strawberry frosted. How many possible ways can the donuts be arranged in the box if they're placed in the box at random? This is another distinguishable permutations problem because, those 5 glazed. It's not like glazed number 1 looks different from glazed number 5. Let's assume they all look exactly the same, right? Blueberry number 1 is going to be the same as blueberry number 3. So those are going to be the same outcome. So what I have here is 5 plus 3 is 8. Another 12? 12 again? Should have chosen a different number. 12 factorial divided by, okay, we got 5, a 2, a 3, a 2, and then a 2. Ooh, yeah, butchering the handwriting there. Okay. All right. So we got that 479 million 001,600 divided by, now watch as I'm going to put this all in at once. We got 5 factorial. Come on. 5 factorial times 3 factorial. Whoa, that's a minus sign. Times 3 factorial times 2 factorial times 2 factorial. $166,320. Those are how many different ways we could randomly put those donuts in the box. Different ways, right? Distinguishable permutations. Ones that look different from the other. That's where it gets its name, distinguishable permutations. Yeah.
That's really weird.
I had a buddy in high school. He spelled his name like that, John.
That's so
John
I don't like it.
Isn't that how John Smith spells his name? Or just-
Daringer.
No.
Shout out, John, if you're watching. I mean, these do get posted on YouTube.
Oh.
I bet he is.
Shout out.
He listens to this.
All right. So what if order matters now? What if order does not matter? What if order does not matter? Well, then it changes from a permutation to a combination. Changes from a permutation to a combination. Order does not matter in this case. Like, I have my students, and I am going to take 3 of them, and they're going to come help me with a task. Does picking 1, 2, 3, where I picked Kate first, 1, 2, 3, is that a different outcome if I picked Gabby first? 1, 2, 3. No, these 3 are still helping me with my task, right? How many different ways could I choose that? Well, that would be total C3. 8 or 9, how many kids are here? Right. That is where order does not matter. Order does not matter. I'm picking things out of my total, and I don't care what order they go into. I'm just kind of like lumping them all together, So the choice here of 1, 2, 3 doesn't change anything if I pick them in a different order. So it's going to cut down on my number of ways I have to produce those things by a lot, right? A permutation is always going to be way more. I don't want to say way more. A permutation is always going to be more than a combination because choosing 1, 2, 3 is the different from 1, 2, 3, 2, 1 in a permutation. But that's the same event in a combination. Okay? So for example here, you had 8 different plants to buy, but only room for 3 of them on a shelf. How many different combinations of plants can you buy on the shelf if order does not matter? Notice my wording change. If order does not matter. If order does not matter. If order does not matter. Okay, so in that respect, I'm going to say that's 8C3. In terms of my formula, I didn't really discuss it, but it's n factorial divided by n minus r factorial times r factorial. So what's the difference between a permutation formula and a combination formula? That guy right there, right? So basically what I have here is 8 factorial divided by 5 factorial times 3 factorial. Or in other words, 8 times 7 times 6 divided by 3 factorial. So I have my permutation divided by basically my repeats that I could possibly have, right? I want to cut down on my repeats. So I'm taking that permutation and I'm dividing away 3 factorial. All of that is to say that you don't really need to memorize that formula. All we need to know is where to find it in our calculators, and it's right below NPR. So 8C3 is 56. There is only 56 ways to do that. I have 8 plants, and I'm choosing 3 of them to go on a shelf, and we're assuming that daisy, cactus, iris is the same thing as iris, daisy, cactus. All right. We have 15 movies at home and want to bring 6 on vacation. How many different combinations of movies can you bring with me? Now, does order matter here? If I choose movie 1 and then movie 2 and then movie 3, does that change if I choose movie 3 first then? No. Right? As long as I'm just bringing them with me and I'm saying, kind of like saying, well, the order in which I watch them, there's no sequels or anything. I'm going to watch them eventually. That's 15C6. Okay. 15C6. 15C6. 5,005 different ways to choose them.
Seuss.
Seuss?
That looks like Seuss.
Find the probability of being, I don't want to do this. I don't want to do that. No, I don't want to confuse you on that because there's no like quiz questions on that, so I just want to focus on what. Okay, this is where it starts to get a little funky because now we're finding different ways to choose things and different ways to, the probability based on that. Because remember, what a general probability rule is: successful outcomes divided by total number of possible outcomes, right? I've got 7 men and 10 women that are members of the PTA. If a 5-person council is formed at random, what is the probability that there will be 2 men and 3 women?
What's the PTA?
Parent-teacher organization.
Organization?
Parent-teacher association. PTO would be parent-teacher organization. Okay, so we've got, now think about this. If I truly want probability, what's my total amount of things that could happen? I'm choosing a 5-person team, right? Does it matter the order in which I pick those people? No. So what's my total number of outcomes? 17 C 5, right? You follow me there? That's my total number of events that could possibly happen. Okay. So now I want to know the successful events. Successful events. I have 7 men. How many am I choosing? 2. And I want to say and, multiplication rule, and I want there to be 2 men and 3 women. So this means multiplication. 10 C 3. Hold on. Yep. You just said it in the bottom. 10 C 3. So I've got 7 C 2 times 10 C 3 all over 17 C 5. See, this is where it starts to get a little weird in terms of the different combinations and permutations that we could have. Okay, so 7C2. 7C2 is 21. 21 different possible outcomes that I could have where I'm choosing the 2 men. 10C3. 120 different possible outcomes that I could have for the women. And then total number of possible outcomes that I could have overall, choosing 5 of them, 6188. So now if I do that, if I run those numbers times 120, so that's 128, divided by 6188, 0.407, 0.41. So you can start to compute probabilities based on that. I think it's kind of good that we're not doing this homework assignment, that I'm just going to give you the test review, because I remember in this homework assignment, there are some questions that deal with like playing cards that get really, really, really messy. Yeah. So if you really want a fun time, go look at the actual homework for this section. Let me give you guys the review sheet.
I'll just write.